Okay, so in this section of the lesson, I wanted to talk about saltatory conduction. And now saltatory conduction has some connected vocabulary that I wanted to talk about very quickly. So saltatory conduction is able to occur because of the existence of myelin sheaths. So again, the term myelin we talked about are the cell membranes of cells. So it's made up of a phospholipid membrane because it's made up of the cell membrane of either schwann cells in the peripheral nervous system or oligodendrocytes in the central nervous system. Now, the cells, either the schwann cells or the oligodendrocytes, wrap around an axon in dozens of layers and therefore sort of insulates the axon. Now, insulation, when I first pictured insulation, I was sort of picturing the insulation on an electrical wire, and it does look like that, but it doesn't really work like that. The way that it works is it prevents the exchange of ions between the intracellular space and the extracellular space. Okay, so what I'm drawing here is a whole bunch of either oligodendrocytes or schwann cells with layers and layers of cell membrane wrapped around these axons. So you can picture it. It wraps, I can't really draw it in 2 dimensions, but it wraps 360 degrees around the axon. Now, what happens is if you have, I'm going to draw next to it, I'm going to draw up here, an unmyelinated axon. Now, with an unmyelinated axon, a action potential is propagated by the sequential opening of voltage-gated sodium ions. So, the sodium ions rush in here. This becomes positive. This becomes negative. That opens up the next one. This sodium ions rush in. This becomes positive. This becomes negative. This opens up the next one, and the next one, and the next one. Okay, and this allows the action potential to travel from one part of the axon to the other part of the axon. But since it has to open so many voltage-gated sodium channels, each one takes, part of a microsecond. So each one that opens takes a little bit more time. Now, what happens with saltatory conduction is there is no way for ions to be exchanged because of the myelin sheaths. So there are no sodium channels, and even if there were, the sodium couldn't get in to these parts of the cell. So there is a cluster of thousands of voltage-gated sodium channels in between these, in between the myelin sheaths, and these areas are called the nodes of Ranvier. So the nodes of Ranvier are these little areas that do not have myelin sheaths. So they take up maybe 1 micrometer when there is like 15 or 20 micrometers of sheathed axon. Okay, so what happens is the sodium ions can't get into any of these areas, but there's sort of because a bunch of voltage-gated sodium ions opened up here, a whole bunch of sodium rushed in. Now, the sodium has to come from somewhere, so it kind of comes from this direction, comes from this direction, a little bit from this direction. But enough of the sodium gets sucked sort of along the edge of the myelin sheath that it changes the voltage polarity of this area here, and that opens up the sodium gate. Sodium rushes in here. Sodium gets pulled from here, here, and here, and this triggers all these sodium gates to open up. Okay, the sodium gets pulled from here, here, and here, and that triggers these sodium gates to open up. Okay, so the propagation of the action potential skips from node to node to node to node. Now, this is sort of akin to, if you've ever been to New York City. I was there a couple of weeks ago. And in New York City, they have two different kinds of trains. They have express subway trains, and they have local trains. Local trains stop every 7 blocks or so. So to go, and express trains maybe stop every 50 blocks. Okay, so there's like 10 times more stops on a local train than there is on an express train. So a local train will stop at, if I'm trying to get downtown from 120th Street, it's going to stop at 114th Street, it's going to stop at 108th Street, it's going to stop at 99th Street, it's going to stop at 95th Street, etc., etc. And finally, I'm going to get to my destination. Now, with the express train, I get on at 120th Street and goes right down to 70th Street, and then the next stop is 42nd Street, and I can get off at Times Square. Okay, so those of you who have been in New York City and rode the subway station can picture this quite exquisitely. Those of you who have not can just imagine it. If you hop on the express train at 120th Street, you're going to arrive at 42nd Street in about 5 minutes. If you get on the local train, that same trip is going to take you more than a half an hour, because each of these stops takes 30 seconds or so, and it's going to add significantly to the time of your trip. The same type of thing is happening. Can be seen in the difference between a non-myelinated axon and a myelinated axon. A non-myelinated axon requires many stops. Lots and lots of voltage-gated sodium channels need to open up to move from one side of the axon to the other. But because of the way that the myelin sheaths work, and the action potential can skip from node of Ranvier to node of Ranvier, just like an express train. This is so efficient that the speed can be up to 50 times faster on a myelinated neuron than it is on a non-myelinated neuron. Okay, so that is saltatory conduction and the way that myelin makes the movement of action potentials much quicker. Now, the other advantage to myelin is because fewer ions are needing to be exchanged here, it reduces the amount of energy used by the nerve cell. Now, if you picture, I'm going to move down here a little bit, over time, when there are many nerve impulses happening over a period of time, it's going to start to have a substantial amount of sodium moved from outside the cell into the inside of the cell. And that is going to have to be pumped out again. And how does it get pumped out? With the old sodium, potassium, ATPase pump. And because more sodium is being moved into the cell, that's going to require this pump to work a little bit harder, and it's going to require more energy to be used. So a non-myelinated cell, because it has more voltage-gated sodium ions, and more sodium is going to be moving from outside of the cell to the inside of the cell to move to propagate one action potential from one side of the axon to the other. More sodium is going to end up on the inside of the cell, and that is going to have to be pumped out, and that's going to increase the use of energy. So a myelinated cell requires the use of less energy.